So you try it yourself. And now I'm going to tell you about a newer method of doing this, which is the my Keel and Kingley methods. It's a long story short. It's developed by political scientists. This might be a newer and more advanced method. I'm already teaching you about it. You might use it in the end. You have to use it for your assignment because I think it's quite cool and neat. So basically, this is the code for the package we call require mediation. We have to then, for this one, we have to sequentially define which one the regression for the mediator, and then the regression for the outcome variable. Yeah, so I've called them met.fit here and out.fit here. And again, it's just a regression, so it's nothing more than a linear model. So it's the same type of commands we've seen before. I've just called them differently. Now, what I should have done perhaps before as well, if you put set.seed, then it will pick a number, and then you're also replicable. It means that if you put that number in, when it does 10,000 bootstraps, you should get the same result as I do. So that's why I put set.seed here, and then I put met.out, which is the output file where I will store the output, which I will then evaluate because it will print lots of output. And then I just use mediate, met.fit, out.fit. I have to tell which one is the treatment variable, and treatment is the same as independent, but it's built also for medical sciences, so you have treatment versus control. So it's looking for a treatment variable. You tell which one is the mediator, and then you tell it whether it wants to bootstrap, and you tell it how many bootstraps it has to do. You can also do, you remember from regression that there were things like robust standard errors when you have heteroscedasticity or other nasty things going on. It can also do all that, but you can't do that for bootstrapping, so that's ignored when you do bootstrapping. So, but it can do all sorts of other fancy things. So it will then print something like this, like if you do summary met.out. So if you just print met.out, then it will just be lots of things because it will store lots of other results also. And then this uses a different type of description. So you have ACME and ADI. And ACME is average causal mediated effect, and ADI is average direct effect. And it will tell you sort of these values are quite close to what we saw with the bootstrapping method that I showed you before, but it's just a different approach. And it will also tell you the proportion of so the total effect. So this one plus this one should sum to the total. So it's quite close to what we had before. And it will also tell us the proportion of which it's mediated. So as you saw before, our coefficient was reduced to 1/10. So intuitively, you might already think that 90% would be accounted for by our mediator. And so what it nicely does is it would then also say whether that proportion mediated is significant, and it will print some values for that. So that could also be quite useful to report. It tells you the sample size, and it tells you the number of simulations to use. So, and those are again confidence intervals for the lower and the upper. Yeah. Okay. And it's using here a percentile method because you remember the different ways of bootstrapping. This one only does percentile. And so if you would write this up, you would say the mediation analysis showed a significant average causal mediation effect, and that's that value, 0.36, and then the 95% confidence interval. So it's this rounded up, the lower confidence interval, the upper confidence interval. But the average direct effect was not significant or no longer significant, so that's that drop that we saw. So first we had a significant effect going from X to Y, but it's no longer significant. And that's 0.04, and the 95% confidence interval goes from -0.2 to 0.3. Yeah. So that's just a different package, and what it can do further is something nice, also like make this type of plot. So this is to plot for a mediation effect, plot for the direct effect, and then plot for the total effect, which is sort of the sum of those two. And this is a long bit of text, really technical. But remember when I told you about hidden confounders and things which can basically explain away our relationship? So it could be that there is no mediation, but there's a third variable which we didn't measure, which explains all paths basically. what this package can do, it can estimate how big that effect has to be in order to explain away all the relationships. And that's quite neat. So it can tell us something which, so simply put, are there hidden or unmeasured confounders, and how big would they have to be? So you can't, because if you didn't measure them, they're hidden or unmeasured, but you can try and estimate how big the effect should be in order for it to annihilate your effect. Yeah, and that's quite a neat thing, I think, to do. Does everybody understand this? So basically, unless in a perfect world where you measured everything, there could be something which you didn't measure, which explains away the proposed mediation effect, and we can do some type of testing to find out how big those effects would be. And that's done by a sensitivity parameter. That's a rho, and it basically corresponds to everything that we didn't measure. We sort of treat that as error, and we're hoping that those errors are uncorrelated in our models. But if they are correlated, so if there is, and that would be the scenario where we have a third variable explaining everything away, how strong would that have to be in order to explain it away? So in an ideal world, rho, or the sensitivity parameter, is 0. So think of step 2 and step 3. Those errors should be uncorrelated in Barron and Kenny. It's assumed to be 0, and people refer to it with rho. So just in case we're unclear why I keep on banging on about rho, rho is the Greek symbol for the correlation between those errors. Yeah. Very simply put, you can read all the maths in the things, but I'm trying to tell it to you in sort of layman's terms as to what is going on. And so under sequential ignorability, so this would be the perfect scenario for mediation. So there are no hidden confounders. Rho is equal to 0, and thus the magnitude of correlation coefficient represents the departure from. So if this is really high, then it means you have correlations, and it means that it explains away some of the effects. So we can try and then guesstimate how big rho should be and what type of effects it has. So we can do a sensitivity analysis, and it's using the command medsense, and basically we take our output object, which we made before from mediate, and then this is just that we want to see steps of 0.05 for rho. You can sort of find the breaking point at which. So we're going to try to find a breaking point at which our mediation effect becomes 0. Yeah. So how big do we have to make rho in order to reduce our mediation effects, these acme effects? Yeah. Lots of abbreviations. Does everybody sort of still understand what is going on and what the purpose is? So here it's printed all different variables of rho, and then we can sort of see where acme becomes 0, and it's crossed this between 0.05 and 0.55. So it's picked out as a number because that's the closest. So we asked it to go into steps, and then we'll pick the step where it crosses over to 0. Yeah. So this one is still not 0, and then so it's using this type of estimate for this. Okay, and then it will have printed some really strange-looking things here, and I'll explain to you in a moment what those are. It's basically the variance explains. So that bit at the bottom, because it's not really properly printed, but the accent circonflexe, as they call it in French, what do you call it? Cap, or how do you call it? How do you call the symbol? What? So in French it's called accent circonflexe. I'm not sure it's so it's basically this accent you get in French, but it basically means put things to the power. So that means r squared, and that means underscore m. So it was sort of, if you translate it to that, that's sort of what it means. And that's the proportion of the previously unexplained variance in the mediator and the outcome variables is required to be explained by the unobservable pre-treatment confounder in order to render the mediation 0. So that's a very long bit of text, but basically how much of the, so we've likely not explained all of the variance, so some of the variance is left. How much of that unexplained variance do we need to explain in order to explain away our mediation effect? That's it. Yeah. That's the technical way of writing it. And so we also have the thing with like the big tilde above it. So that's the thing at the bottom. And I think that's usually the one that is more interpretable. So this is how much of the previously unexplained variance we need to have explained away in order to explain away our causal effect. And this is telling us something else. This is telling us how much of the proportion of the original variance, basically the bit we've done, has to be explained by an unobserved confounder in order to render our mediation effect 0. Yeah? And so that's 0.1395. So these are R-square values. So basically 13% of the variance, that could be a lot or not a lot, depending on how you talk to. But if that was caused by a hidden variable, then our analysis would be implausible or wrong. Yeah. So we're looking hopefully for quite large values here. Yeah. So we need quite a large effect for unmeasured variables to explain away this really strong relationship. Does that make sense? So this is quite neat because it sort of tells you how much of the unexplained variance you would have to explain in order for your model to be false. And I think that's something extra that you can put in your reports. So now we're coming to the end. So some critiques about path analysis, and we'll pick this up further because we'll also look at doing path analysis with structural equation models because everything is regression, and structural equation models are again another way of doing regressions. And we'll come to that later. But we could test potentially many different models. So if you measure 10 or 15 variables, you could build all sorts of arrow models, and they could all have significant paths. But then you would be able to decide between them. So there might be a model which equally fits well. So if we had a model, so now we've drawn one with a path, but there could be a model where we just have all of them at the same thing, all going to the outcome variable. Is that model a better model or a worse model? So we didn't address any of that. We just tested whether these causal pathways work, but we didn't test which one is the better fitting model, whether a model with just main effects does equally as well as one with causal effects, or whether they are significantly worse, significantly better, or the same. And we'll come to that when we talk about structural equations. And the key lies in model fitting and trying to compare the relative fit of one model versus the other one. So here we've just taken a theoretical model and just drawn the arrows and then looked at the significance, but we haven't done any type of model comparison between models. Yeah. So when fitting multiple mediators, what will happen is it will average all the paths. So if you have like some junk variables, so if you put in, so we've today focused on one, just having one in the middle, but you could have, and for the exercise, you will have one with 2 in the middle. If you have 3 or 4 in the middle, you could have a significant mediation, but it could be entirely driven by one of those 3. Yeah, and so it doesn't really tell you which one then is really important. And so again, we use structural equation models to see if we take away a path, whether the model becomes significantly worse, and that will really tell us if we have lots of mediators, which one does the job and which ones are just along for the ride and not contributing a lot to explanation. They're just there. Yes. So when fitting multiple mediators, remember acme is average, so it will just be averaged across all those mediators. So if you put in 3, it will be the average of those 3 in the middle. And so you could have a scenario where you then mistakenly think, yes, we have mediation, but it's driven really by one variable, and all the other variables you hypothesized about are really not that important. So you would make an error in that case. So I think that's all I have to cover. So for once, I'm very much on time. So that's good. So if you want, you can start working on the exercise, and I can be around here, or you can leave if you prefer to leave. But you can feel free to start working, and I can answer some questions about the exercise. So basically, I want you to download the data which are on blackboards. It has real life data from 95 women. They performed various skills relating to body image, and they also had their BMI measures. And they're asked to make a mediation model by the causal steps method that you've done. I want you to make a diagram, and then I would like you to calculate this overall z-test and report it. I would like you to test the mediation via the bootstrapping, Preacher, and Hayes method. And then I would like to test the mediation model with 2 mediators, but with the same independent and dependent variables. And then I would like you to export a figure of that mediation model, as I've done. So that diagram that you saw, export it. I would like you to test the mediation via that novel methods that I've shown you, via Acme and ADDIE. And you would have to do it sequentially because you can't do 2 mediators at the same time if they are not continuous. So you might have to do it one at a time and then evaluate them. But I'll show you the results when you submit the things. And then I'd like you to perform a sensitivity analysis, as I've shown you. Basically find out how big the correlation between the errors, or how big the unmeasured hidden variable has to be in order to explain away the hopeful mediations you will find in your analyses. So it's up to you if you want to continue work a little bit, but it might have been quite a lot to take in. Also, if you have any questions, now's the time to ask. Not about the assignments, because that has to be in Blackboard for the ones who are not here. So it's just not because I'm cruel, but it's just because it's a little bit unfair to them. Who's going to work here and who's going to head off and drink coffee? Go home? No takers? Okay, good luck, and start working on the exercises and the assignments, and see you all next week.
Well, I never. How do you push it? You literally